We already know that a relation maps input values of its domain onto output values of its range. If we look at the mapping to the right, we can see that A is paired with 3, so that would give me A comma 3. B is paired with 1, so that would give me B comma 1, and C comma 2. Well, we have what's called the inverse relation, which kind of undoes the relation and maps output values back to input values. So if the original mapping is called F, then we see right under it, we have a mapping that is F inverse. So this symbol right here, it's F inverse, F inverse. Okay? And so notice the ordered pairs are switched. So instead of having A comma 3, now we have 3 comma A. And instead of having B comma 1, now we have 1 comma B. And instead of C comma 2, now we have 2 comma C. So what happens is the domain and the range are switched. The range of the original function is now the domain of the inverse, and the domain of the original is now the range of the inverse. So that gives us the definition of an inverse relation. An inverse relation is what we get when we switch the domain and the range. So if we look at these graphs, we can start with the one on the left. We have 5 ordered pairs with this relation that I know. So I'm going to switch the domain and the range. In other words, switch the x and the y and see what kind of graph I get. So I'm going to start with 4 comma 4. And if I switch 4 comma 4, I still get 4 comma 4. If I switch 0 comma 3, I get 3 comma 0. If I switch negative 1, 1, I'm going to switch the x and the y. So I get 1 comma negative 1. And if I switch the negative 3 comma 0, I get 0 comma negative 3. And if I switch negative 4, negative 2, I get negative 2, negative 4. So if I connect these points, I draw this graph, I notice it's exactly the same shape as the original graph, except we actually have a reflection. We have a reflection over the line y equals x. Let me change my color. We have a reflection over the line y equals x. So I'm going to draw the line y equals x. Here it is. It's a line that goes through the origin, has a slope of 1. So there's the line y equals x. And notice, if we take the black graph, we reflect it over the line y equals x, we get the new blue graph, which is the inverse of the relation. So notice, also, we can also look at these other graphs and notice how its inverse, the symbol, remember the symbol, if our original function is called f, then the inverse of that function will be called f inverse. And that looks like a negative 1 exponent, but it's not. It's actually just the name of the function, f inverse. That's what we say. So notice for all of these graphs, if we take the inverse, will always be the reflection over the line y equals x. Okay, so if the relation is described by an equation rather than a set of ordered pairs, then we can easily switch the x and the y in order to get the inverse. So let's look at these equations. We're going to start with letter A. We're going to find the equation for the inverse of each relation. We're going to graph on our calculator. We're going to look at that, and we're going to talk about domain. So if f of x is equal to negative 3x plus 1, if we go to our calculator, go to y equals, we'll put in negative 3x plus 1. We know what that looks like. We know we're going to get a line with a negative slope. So now I'm going to find the inverse. So I'm going to write y equals negative 3x plus 1, and then I'm going to switch the x and the y. So x equals negative 3y plus 1. And after I switch the x and the y, I'm going to solve for y. So those are the two big steps. The first step is you switch the x and the y. And the second step is to solve for y. So I'm going to subtract 1 from both sides, and then I'm going to divide by negative 3. So I get y equals negative 1/3 x plus 1/3. And the last thing I'm going to do is I'm going to give this inverse its correct name. So since the original equation was called f of x, I'm going to call this inverse f inverse of x. Okay, and if we look at this graph, we look at the graph of the inverse together, negative 1/3 times x plus 1/3 like that. And we can see they don't really necessarily look like reflections, but if I draw my line of reflection, I'm going to go down to y4, and I'm going to draw my line of reflection. My line of reflection is the graph y equals x. So these two graphs are reflected over the line y equals x. Okay, so let's do letter B, and when we look at the graph of this one, it's going to be a little more obvious. So I'm going to write y equals 1 minus x squared, and then I'm going to do two things. I'm going to switch the x and the y, and then I'm going to solve for y. So I'm going to say x equals 1 minus y squared, and then I'm going to solve for y. So I'm going to subtract 1, from both sides, and I'm going to change the sign now because I have a negative y squared. So I'm going to say y squared equals, instead of x minus 1, I'm going to say 1 minus x. And then I'm going to take the square root of both sides. And when I take the square root of both sides, I have to remember the plus or minus or I won't get the whole graph. Okay. So instead of calling it y, I have to give it its proper name. Since my original equation is called g of x, then I'm going to call this one g inverse of x. Okay, let's go to the graph and let's talk about domain here. If we go to the graph, I'm going to get rid of the one from last time. And I'm going to put in my original, which is 1 minus x squared. So there's, oops, let's clear that. 1 minus x squared. That's g of x. And then the inverse has two parts. It has a plus or a minus. Your calculator will not do a plus or a minus. The TI-84 does not do a plus or minus. So you have to do it as two separate graphs. So I'm going to do the square root of 1 minus x. Make sure that's right. Square root of 1 minus x. And then I'm going to go down to y3. And I put in negative square root of 1 minus x. Notice what I did was for y2 and y3, I changed the color to be the same because it's actually the same graph. So when I press graph, there's the original, there's the inverse, there's my line of reflection. So it's easy to see that when we reflect a parabola over the line y equals x, it turns it over on its side and becomes a sideways parabola. So I want you to notice two things. First notice that the original g of x is a function. We do our vertical line test. The original g of x is a function. But if I look at the inverse of g inverse, it is a sideways parabola, and a sideways parabola is not a function. So the first one we did with the two lines, the original f of x is a function, f inverse is a function. But when I went to letter B, my original g of x is a function, but my g inverse is not a function. Okay, let's go to letter C. So we're going to change the j of x to y. Y equals the square root of 2x minus 3, and we're going to switch the x and the y. X equals the square root of 2y minus 3. Now I'm going to solve for y. So in order to solve for y, I need to square both sides. So I'm going to say x squared equals, when I square a square root, the square root goes away. So then I'm going to add 3, and I'm going to divide by 2. So instead of calling it y, I'm going to call it the inverse of j. Since my original equation was called j of x, this one's going to be called j inverse of x. And there's my inverse. Okay, so now let's go to the graph, and we have to talk a little bit about this. Okay, so I'm going to clear these graphs, and I'm going to put in the original square root of 2x minus 3. So I know the domain here. The domain here is going to be greater than or equal to, I'm going to leave my line of reflection. The domain for this function is whatever makes the number inside the square root 0. X must be at least that number. So x must be at least 3/2. And notice it's just one little bitty curve here. Okay, so if I put in the inverse, which was, let's check, x squared plus 3 all over 2. So if I put in the inverse, I'm going to make a fraction first. Make a fraction. I'm going to put in x squared plus 3 all over 2. And I look at this, I get a whole parabola, don't I? Yes, I do. But what I want you to notice is that the only part of this parabola that is actually the inverse of this blue graph is the red part where x is on the positive side. So where x is greater than or equal to 0. That's what gives me my reflection. So the reflected part of this blue graph is going to be just this part right here of this red graph. So what we have to do, what we have to say when we give the inverse, is that j of x is equal to, let's rewrite it. We're going to write j inverse of x is equal to x squared plus 3 all over 2 when x is greater than or equal to 0. That's what we want to say, because we just want the positive part of that graph, not when x is negative. Okay, we're going to do one more. So k of x equals, so we're going to make it y equals 2x cubed plus 5. And I'm going to switch the x and the y. So x equals 2y cubed plus 5. I'm going to subtract 5. I'm going to solve for y now. So I'm going to subtract 5 and divide by 2. And after that, I need to take the cube root of both sides. So I'm going to write y equals the cube root of x minus 5 all over 2. Not really concerned about simplifying here. And instead of calling it y, we're going to call it k inverse of x. Okay, so we noticed sometimes the inverse relation was a function. Sometimes the inverse relation was not a function. So what we can do is we can do the horizontal line test. We know what the vertical line test is. The vertical line test tells us whether a relation is a function or not. Well, the horizontal line test on the original function's graph will tell us whether or not the inverse is a function. So if we draw horizontal lines and only go through one point every time, then what that tells me is that the inverse of the relation is a function. So what this indicates is a new definition. It indicates what we call a one-to-one function. A one-to-one function is when a relation is a function and its inverse is also a function. So if the graph passes, the original graph passes the horizontal line test, then that indicates that not only is each x paired with exactly one y, but also each y is paired with exactly one x, and that's what indicates a one-to-one function. So look at the two examples. I give an example of something that is a one-to-one, y equals x cubed, is a one-to-one function, because first of all, it passes the horizontal line test. And so what that tells me is that each y is paired with exactly one x. Not only is this a function, so I'm doing my vertical line test, and it's definitely a function, but it also passes the horizontal line test, which tells me it is also a one-to-one function. Notice the square root function, the absolute value function, does not pass the horizontal line test. Therefore, it is not a one-to-one function. So furthermore, if a function is one-to-one, then the compositions, when you do a composition with a function and its inverse, it will equal to x. So let's see what we're talking about. So we're going to try these. We're going to verify that f and g are inverses. So what I'm going to do is I'm going to do the composition f of g of x, and then I'm going to do g of f of x. And I'm going to show that I get x both times. So I'm going to do f of g of x first. So that's going to be 2 times 1/2 x plus 2, and 2 times 1/2 x plus 2, and then minus 4. And g of f of x is going to be 1/2 times 2x minus 4 plus 2. And so when we simplify these, we see that we definitely get x there. And when we simplify this one, we get x also. So this is our proof. Our proof that these two functions are inverses of one another. So you can do the next example and do exactly the same thing, and you can see that when you do f of g of x and when you do g of f of x for both of these functions, and if you get x both times, if your composition simplify to x both times, then that shows that these two functions are inverses of each other.